Welcome to the week 7 of Swayam course on Introduction to Electric Vehicles and Hybrid Electric Vehicles. Myself, Dr. Venu Sonti, Assistant Professor in National Institute of Technology, Raipur. In the last week, we have discussed about the construction and working of permanent magnet synchronous motor along with its speed control techniques. In today's lecture, we will cover about the construction, working and speed control techniques of brushless DC motors. The DC motors have been favored for applications requiring precise speed or position control owing to their straightforward control mechanisms, which are considerably simpler compared to those of alternating current motors. This inherent simplicity makes DC motors an attractive choice for a wide range of control tasks. However, their design includes brushes and commutators which necessitate the regular maintenance. This requirement for periodic upkeep has led to a decline in their use in various motor drive applications, particularly those demanding continuous operation and high system reliability. As a result, the preference has shifted towards alternatives that offer more durability and less frequent maintenance. To address the maintenance challenges associated with the DC motors, the brushless DC motors was developed in 1962. This innovative motor retains the favorable electrical characteristics of traditional DC motors while significantly enhancing reliability by substituting mechanical commutation with electronic commutation. In a BLDC motor, this electronic commutation is achieved through the use of sensors and driving circuits. The sensors are responsible for detecting the precise position of the magnets on the rotor. Based on this positional information, the driving circuits are able to selectively energize specific windings, thereby facilitating continuous and efficient rotation. This design not only eliminates the need for brushes and commutators, but also improves the motor's overall durability and performance, making brushless DC motors a superior choice for applications requiring sustained reliability. In brushless DC motor, the elimination of brushes found in traditional DC motors is achieved by placing the armature windings on the stator and magnets on the rotor. This design creates a distinct configuration compared to DC motors. The flexibility offered by this design allows for various configurations of brushless DC motors, enabling them to meet a wide range of application needs. Brushless DC motors offer numerous advantages such as high efficiency, high power density, an excellent torque to inertia ratio, the capability for high speed operation, a simple drive method and cost effectiveness. Consequently, they have become widely adopted as cost effective solutions in numerous applications like light electric vehicles. Next, coming to the construction of brushless DC motors. The brushless DC motors can be classified based on the number of stator windings. Based on the number of stator windings, they are classified as single phase brushless DC motors, two phase brushless DC motors, three phase brushless DC motors and multi phase brushless DC motors. Single phase brushless DC motors are commonly used in household appliances and small machinery due to their straightforward design, simple driving circuit and low cost. However, these motors can only rotate in one direction and have a detect point where no starting torque is generated, necessitating additional components for startup. The starting torque is typically provided by reluctance torque, which results in a significant cogging torque. Single phase brushless DC motors are well suited for small power applications such as fans, blowers, where a low starting torque is acceptable. Multi-phase brushless DC motors with more than 4 phases are primarily used in aerospace and military application. The reason for this is they have the increased power density and fault tolerance capabilities. Among various BLDC motors available, the 3-phase brushless DC motors are most prevalent. The brushless DC motors can also be categorized by the direction of magnetic flux into radial flux and axial flux types. In radial flux motors, the flux from rotor magnet crosses the air gap radially, whereas in case of axial flux motors, the rotor magnet crosses the air gap axially. The radial flux motors have been traditionally more widely used and come in two categories, inner rotor and outer rotor. The inner rotor design, the most common type, features higher heat dissipation capacity, a high torque to inertia ratio and a low rotor inertia, making it ideal for servo drives that require a quick dynamic response. The cylindrical rotor with a shaft mounted bearing configuration minimizes vibration and acoustic noise. Outer rotor motors have rotor magnets that rotate around stator windings located in the iron core of motor, resulting in relatively high rotor inertia. This design is advantageous for applications requiring constant speed operation. The outer rotor motor can utilize more magnetic material than the inner rotor design, allowing for higher flux even with low energy product magnets. This motor type is increasingly used in applications such as computer disk drives, cooling fans and washing machines due to its high speed operation capabilities and benefits of magnets affixed inside the yoke. Next, coming to the working of brushless DC motors. The fundamental operating principle of a brushless DC motor involves sequentially energizing the faint windings based on rotor's permanent magnet position to produce continuous torque. Crucial to this process is accurate information about rotor magnetic position, typically obtained by using Hall effect sensor. To explain the working of brushless DC motors, let us consider a 2-pole 3-phase star connected BLDC motor drive system as shown here. In this system, you can see a 3-phase inverter. The DC supply VDC is connected to the input of inverter and the output of inverter is connected to the stator windings of the BLDC motor. You can see here this is a 3-phase inverter which is having 3 phases A, B, C. The switch T1 is the upper switch in A phase and switch T4 is the lower switch in A phase. The switch T3 is the upper switch in B phase and switch T6 is the upper switch in B phase, is the lower switch in B phase. The switch T5 is the upper switch in C phase and switch T2 is the lower switch in C phase. The output of the inverter is connected to the stator windings of the BLDC motor. On the stator windings, the 3 Hall effect sensors H1, H2, H3 are connected in such a way that they are phase displaced by 120 degrees. The output information of the rotor is given to the controller, and from the controller the gating pulses are generated depending upon the speed command and direction command. In this way the BLDC motor will work. Now if you see the operation of this BLDC motor, let us assume that the rotor position in such a way that the north pole of the rotor is pointed towards the Hall effect sensors H1 and H3 and the south pole is pointed towards the Hall effect sensor H2. Whenever there is a north pole towards the Hall effect sensor, then the output of Hall effect sensor will be 1. So now in this position the outputs of Hall effect sensors H1, H3 is 1 and the output of Hall effect sensor H2 is 0. Now if you turn on the switch T1 and switch T6, then the windings A and B are connected to the supply VDC. A is connected to the positive of the VDC and B is connected to the negative of VDC. Here you need to observe that the winding C is left unexcited and the current I will flows from winding A to winding P. Because of this flow of current, a south pole is created on the winding A and a north pole is created on the winding P. Due to this pole formation, now the rotor will rotate in the counterclockwise direction and comes to a new position as shown here. In this new position, now the north pole is pointed towards the Hall effect sensor 1 and south pole is pointed towards the Hall effect sensors 2 and 3. Here the output of Hall effect sensor H1 is 1 and output of the Hall effect sensors H2, H3 is 0. In this position, now if you turn off the switch T6 and turn on this switch T2, then the windings A and C are connected to the supply. The winding A is connected to the positive terminal of VDC and the winding C is connected to the negative terminal of VDC. Here the winding B is left unexcited and the current I will flows from winding A to winding C. Now if you see here, because of this flow of current, a south pole is created on the winding A and a north pole is created on the winding C. Due to this pole formation, now again the rotor will rotate in the clockwise direction and come to this third position. In this third position, now the rotor of BLDC motor is pointed out towards the Hall effect sensors H1, H2 and the south pole of the BLDC motor is pointed towards the Hall effect sensor 3. So in this position, the output of H1 and H2 is 1 and the output of H3 is 0. Now in this position, if you turn off the switch T1 and turn on this switch T3, then the windings B and C are connected to the supply. Here the winding A is left unexcited. The winding B is connected to the positive of the DC supply and winding C is connected to the negative of DC supply. Here the current I will flow from winding B to winding C. Because of this flow of current, a south pole is created on the winding B and a north pole is created on the winding C. So due to this pole formations, now the rotor of BLDC motor again rotates and comes to the fourth position. So in this fourth position, now the north pole is pointed out towards the Hall sensor 2 and south pole is pointed out towards the Hall sensors 1 and 3. As a result, the output of Hall sensors 1 and 3 are 0 and the output of Hall sensor 2 is 1. Now in this position, if we need to turn off the switch T2 and turn on the switch T4. Because of this, the windings A and B are now connected to the DC supply. Here you need to observe that A is now connected to the minus VDC and minus terminal of VDC and B is connected to the positive terminal of VDC. This case is quite reverse to the first case. Here the current I will flow from winding B to winding A. Due to this flow of current, a south pole is formed on the winding B and a north pole is formed on the winding A. Due to this pole formation, again the rotor of BLDC motor rotates and comes to the new position, that is the fifth position. So in this fifth position, now if you see, the south pole of the BLDC rotor is pointed out towards the Hall sensor 1 and the north pole of the rotor is pointed out towards the Hall sensor 2 and Hall sensor 3. In this case, the output of Hall sensor 1 is 0 and the output of Hall sensor 2 and Hall sensor 3 equal to 1. In this position, now if you turn off the switch T3 and turn on the switch T5, the windings C and A are connected to the supply. Here the winding B is left unexcited. The winding A is connected to the negative of VDC and winding C is connected to the positive of VDC. Here the current will flow from winding C to winding A. Because of this flow of current, a south pole is created on the winding C and a north pole is created on winding A. Due to this pole formation, again the rotor rotates in the counterclockwise direction and comes to the sixth position. In this sixth position, now the south pole of rotor is pointed out towards the Hall sensors 1 and 2 and north pole is pointed out towards the Hall sensor 3. As a result, the output of Hall sensor 1 and 2 is equal to 0 and output of Hall sensor 3 is equal to 1. Now, in this position, if you turn off the switch T4 and turn on the switch T6, then the windings C and B are connected to the supply. Here the winding A is left unexcited, the winding C is connected to the positive terminal of DC supply and winding B is connected to the negative terminal of DC supply. The current I will flow from winding C to winding B. Because of this flow of current, a south pole is created on the winding C and a north pole is created on winding B. Due to this pole formation, again the rotor rotates and come to the first position. So, now if you observe clearly, there is a 6-step operation in this BLDC motor drive. Now, if you observe the switch conduction period here, the switch T1 in the A phase is turned on from 0 to 120 degrees and the switch T3 in the B phase is turned on from 120 to 240 degrees and the switch T5 in C phase is turned on from 240 to 360 degrees. Next, the switch T4 in A phase is turned on from 180 to 300 degrees and switch T6 is turned on from 300 degrees to 360 degrees and 0 to 60 degrees, and next T2 in C phase is turned on from 60 degrees to 180 degrees. So, if you carefully observe here, each switch is conducting for 120 degrees. So, in case of BLDC motor drive, the inverter will operate in 120 degrees conduction mode. Next, if you see the waveforms of back EMF and phase current here, now to understand this waveform, let us consider the back EMF waveform of phase A. So, now if you see here, during the 0 to 120 degrees, the switch T1 in the A phase is turned on. So, because of which the A terminal is connected to the positive of VDC. Due to this, an induced EMF of E is induced in the stator winding, and during the interval 180 to 300 degrees, the phase A is connected to the negative of VDC. So, because of which the induced EMF here will be minus E. So, during the instant, that is from 120 degrees to 180 degrees, the winding A is left unexcited. During this, the induced EMF in the stator winding is changed from plus E to minus E, and from 300 degrees to 360 degrees, the induced EMF in the A phase A winding is changed from minus E to plus E. As a result, you can see here there is a trapezoidally induced EMF in the stator windings in case of brushless DC motors. Now, if you observe the waveform of the current, here the current will flow through the winding during 0 to 120 degrees in the positive half cycle, and the current will flow from the windings from 180 degrees to 300 degrees, and that current will be minus I. Because of this, here we have a quasi square waveform. Like this, you can get the waveforms of back EMF for the phase B and phase C. Now, if you want to calculate the power output of BLDC motor, then the power output of BLDC motor is equal to EA into IA plus EB into IB plus EC into IC. The motor torque output is given as power output by omega m. So, this is the expression for the motor torque output in case of BLDC motor. Next, if you see this motor configuration have many merits over the DC motors. Compared to the heavy rotor DC motor containing many conductors, BLDC motors have low inertia rotor. Therefore, the BLDC motors can provide a rapid speed response. Moreover, here in this BLDC motors, the windings are placed on the stator side, because of which the stator can easily dissipate heat, allowing BLDC motors to have a better attainable peak torque capability compared to the DC motors, whose maximum current is limited to avoid the demagnetization of magnets. In addition to this, BLDC motors can operate at higher speed because of non-mechanical commutation devices. Next, if you compare this BLDC motors with the PMSM motor, here in case of BLDC motor, the induced EMF is in the trapezoidal shape, whereas in the PMSM motors, the induced EMF is sinusoidal. In case of BLDC motor, the stators have concentrated winding, whereas in case of the PMSM motors, the stator have distributed winding. Due to this concentrated winding on stator, in case of BLDC motors, we have the quasi-square waveform current, and due to the distributed winding on stator, in case of PMSM motor, we have the sinusoidal waveform of stator current. Next, the inverter that is used to drive BLDC motor normally operates in 120 degrees conduction mode. For PMSM motor, the 3-phase inverter normally operates in 180 degrees conduction mode. Next, if you see the drive method, the drive required for this BLDC motor is simple and use the low cost Hall effect sensors. But for PMSM motor, we require a high resolution position sensor such as encoder, which makes the drive system complex. But the major drawback with the BLDC motor is like there is a significant torque ripple when compared to the PMSM motor. So, this is the major drawback of the brushless DC motors. Now, if you see the speed control techniques of the brushless DC motor, so this is a simple speed control technique of BLDC motor. Here we are going to sense the rotor speed omega m. This value is compared with the reference value omega star. Both these inputs are given to a speed controller. This speed controller here is a simple PI controller. The output of this speed control is a voltage reference V star. Using this voltage reference V star, the PWM generator will generate the gating pulses of inverter. Here, whenever there is a small change in the reference speed omega m star, the voltage reference V stars will change in a large value. Due to this, there are high transient currents drawn by the motor. In order to limit the high transient currents, a current controller also needs to be included in this system. So, now if you see here, this is the modified speed control technique for brushless DC motors. Here in the outer loop we have a speed controller in which we are going to compare the actual speed with the reference speed. The output of this speed controller is a current reference. So, this current reference is compared with actual current, and the output of current controller is the voltage reference V star. Using this voltage reference V star, we are going to generate the PWM pulses, and these PWM pulses are given to the inverter. Now, the inverter will drive the BLDC motor in such a way that desired speed is obtained by controlling the current I. Next, coming to the pulse width modulation techniques of brushless DC motors. In BLDC motor drives, there are two conventional PWM techniques for generating the motor applied voltages. The first one is the bipolar switching method, and second one is the unipolar switching method. In case of bipolar switching method, here the PWM pulses are applied to the all switches in two phases. But in case of unipolar switching method, the PWM switches are applied to the switches of one phase, while one switch of the other phase is kept in the on state. In case of bipolar PWM method, the output voltage of the inverter will be plus VDC or minus VDC. And next, if you see, this bipolar method is simple and have the better transient response when compared to the unipolar method. But the main issue with this bipolar method is there is a high current ripple and there are high switching losses when compared to the unipolar switching method. Next, coming to the unipolar switching method. In unipolar switching method, the switching losses are minimized by keeping one switch turned on. Next, here the applied voltage for the phase windings is 0 and plus VDC or 0 and minus VDC. Because of these voltages, the current ripple is reduced to half when compared to the bipolar switching method. But the main issue with this unipolar switching method is like there will be additional circulating currents in the inactive phase windings. Next, if you see this unipolar switching method, again there are 4 schemes in this unipolar switching method. The first one is the upper switch PWM scheme, second one is lower switch PWM scheme, third one is ongoing switch PWM scheme, and fourth one is offgoing switch PWM scheme. In case of upper switch PWM scheme, the PWM signal is applied for only the upper switch, while the lower switch is kept in the turn on state. Next, coming to the lower switch PWM scheme, in case of lower switch PWM scheme, the upper switch is kept in the on state, while the PWM pulses are applied only for the lower switches. Next, if you see the ongoing PWM scheme, you see the conduction of switch is 120 degrees. So, there will be a first part from 0 to 60 degrees, and second part from 60 to 120 degrees. In case of ongoing PWM scheme, the PWM pulses are applied for first part, that is from 0 to 60 degrees, and from 60 to 120 degrees conduction interval the switch is kept turned on. In case of off-going PWM scheme, the PWM signal is applied for the later part of 60 to 120 degrees conduction interval, while in the first part, that is from 0 to 60 degrees, the switch is kept turned on. Next, coming to the sensorless control of the BLDC motor drive. The main issue with the BLDC motors is use of Hall effect sensors. So, due to the usage of Hall effect sensors, the system is become complex and costly. In order to make the system economical, the Hall effect sensors needs to be avoided. So, for that we need to go with the sensorless control of BLDC motor drive based on the back EMF. Now, if you carefully observe the shape of the EMF, the shape of the EMF is trapezoidal. So, you can see here there is a zero crossing interval whenever the back EMF change from plus E to minus E and from minus E to plus E. Now, if you use a zero crossing detector, so this zero crossing will detect the zero crossing instant. Now, if you trim the 30 degrees during the starting and end of the pulse, then we will get the pulses for switches. In this way, the pulses for inverter are generated in case of the sensorless control. In this EMF detection scheme, we have a EMF detection circuit per phase. So, here we are going to detect the EMF of each phase, and based on that we are going to generate the pulses. The main drawback with this method is like there will be some noise induced in this EMF detection circuit. So, there will be again a torque ripple. Next, coming to the torque speed curve overview. Here the torque speed curve of BLDC motor typically shows how the torque varies with speed. Unlike the brushed DC motor which have linear torque speed relation, BLDC motor exhibit a more complex behavior due to their electronic commutation and control systems. Now, if you see this speed torque characteristic, here we have a constant torque region. At low to medium speeds, BLDC motors operate in the region where torque is nearly constant regardless of the speed. This constant torque region is a result of linear relationship between the armature current and the produced torque. Next, there is a low speed range. At low speeds, BLDC can deliver high torque. The torque is directly proportional to the current supplied to the windings, and speed is controlled by adjusting the applied voltage or current. Next, coming to the high speed, as motor speed increases, the available torque decreases. This is due to the back EMF increasing with speed, which opposes the applied voltage and reduces the current, thereby limiting the torque. Next, coming to the efficiency of BLDC motors. Efficiency is a measure of how well motor converts the electrical energy into mechanical energy and is calculated as the ratio of mechanical power output to the electrical power input. The efficiency of BLDC motor is influenced by several factors. First one is the mechanical efficiency. This refers to the efficiency with which the motor's mechanical components convert electrical energy into rotational motion. It is affected by friction in bearing, windage losses and other mechanical losses. BLDC motors typically have high mechanical efficiency due to their brushless design, which reduces the frictional losses. Next, coming to the electrical efficiency. This involves the efficiency of electrical components including the winding and electronic commutation system. Electrical efficiency can be affected by the resistance in the winding and performance of motor controller. BLDC motors are known for their high electrical efficiency because the absence of brushes eliminates the brush wear and related losses. Next, coming to the magnetic efficiency. Magnetic efficiency is related to the efficiency of magnetic field generated by motor permanent magnets and how effectively this field interacts with stator winding. High quality magnetic materials and optimal design will improve the magnetic efficiency. Next, coming to the overall efficiency. The overall efficiency of BLDC motor is product of mechanical, electrical and magnetic efficiencies. It is influenced by the design of motor the quality of materials and operating conditions. BLDC motors often exhibit efficiencies in the range of 85% to 95% depending upon specific design and applications. With this, I am going to conclude the lecture on brushless DC motors. Thank you.